Section 15.3, we continue study of 3D figures, and one of the most common ones with circles is a sphere. So this is just the set of all points in three-dimensional space that are equidistant from a single point. So just as we had in two dimensions, we identify a single point in the center, and that we call the center, and we say that all points are equidistant from that. Okay, and so in terms of volume and surface area, these are actually well defined, and this is for volume, the value of the volume, or the formula to determine the volume of the sphere is 4/3 pi r cubed. Surface area is 4 pi r squared. Okay, so one property that the book discusses, and it is actually a pretty good property, is that if you pass a plane through the interior of a sphere, then the intersection of the plane and the sphere is a circle. So to kind of study this in more detail, I'm going to do a proof, okay? And so I'm going to start with drawing a sphere. Okay, so here's my sphere, and something like this. Okay, and now what I'm going to do is I'm going to take a plane and pass that through here. So again, I need to draw a sort of parallelogram that passes through the sphere. Okay, and what I need to do is I need to identify, okay, if this is the center of the circle, or center of the sphere, I'm going to call that O, and we determined before that the closest distance between a plane and a point is is given by the foot of the line segment, of the perpendicular line segment to the plane. So I'm going to identify that point as x. So I know that this is perpendicular. Okay, and now what I want to do is consider a point that is on the intersection of the sphere and the plane as, say, maybe point A. Okay, so again, if I just kind of draw this out, I would expect that there would be some sort of this. It's not going to look like a circle from this angle, but I would expect that there would be a circle here that I cut. Alright, so now if I look at this in a little bit more detail, so I look at XA. Okay, so this distance in here. Well, let's see, I have two sides of an angle that I know is 90 degrees, and well, we like triangles, so we're going to make a triangle out of this. And so this is a right triangle where I have OA squared is equal to XA squared plus OX squared. Okay, and I know, well, the distance from O to A is on the sphere, so I know that distance is just R. So I can say R squared is equal to XA squared plus OX squared. Okay, and I rearrange it, and what I'm thinking is I'm thinking that X is going to be the center of this circle. So I want to actually solve for this distance, and I'm wanting to actually show that XA is going to be a constant distance. So I'm going to solve for XA. And so XA is going to equal the square root of R squared minus OX squared. Okay, that's fine and dandy. But now how do I prove that this distance is the same for all points? Well, take another point, okay, in general. Okay, don't pick out a specific point, but just take another point in general. So it's going to be really hard here, but I'm going to identify another point on the intersection of the sphere and the plane as point B. Okay, this green point here is going to be point B. So let's see if I can label that. And again, that distance, I'm going to set up another right triangle so I know that the distance OB squared is equal to BX squared minus or plus OX squared. Again, I want to solve for BX and see what that quantity is, and I know OB is a radius, so arranging this, BX is going to equal the square root of R squared minus OX squared. Same distance, right? So these two are the same. Okay, so I can say without loss of generality, okay, that any point on the intersection is square root of r squared minus ox squared from x. Okay, and so what this leads to is that x is the center of a circle. Okay, and that line, or that was on the intersection, so I can say that from this, the intersection is a circle. Okay, and that is done. Okay, this is a little different than what the book does. Not too different, but a little different. And then one other note in terms of vocab here, if that plane passes through the center of the circle, we actually say that that circular cross-section that is made is called a great circle. Okay, so it would have to be that, it cuts through the center, so we get the diameter of the sphere being the diameter of that circle that is made for that cross-section. Okay, so working through some examples quick here. So a sphere is inscribed inside of a cube, okay, and then another cube is inscribed inside that sphere. Okay, and so all 8 vertices of the second cube are on the surface of the sphere. We know that the radius of the sphere is 6. We want to find the volume of each. Okay, so first of all, I encourage you to pause the video and attempt this on your own. Second, if you want to kind of continue here, what I'm going to do is I'm going to break it into 2 parts. I'm first going to consider the big cube. So again, here's my big cube. Okay, I'm going to draw this the best that I can free-handed. Okay, here's my cube. Okay, and then inside this I have a sphere. So I'm thinking here's the top, sides. Okay, and then I'm just going to kind of sketch a great circle here. And what I know is that the radius of this thing is 6. So the distance and all these sides are tangent. So this is 6, and then I can also say that this distance to the edge is 6. Here's the center. Okay, so really what I'm saying is if this sphere is tangent to all 6 faces, that means that it meets each box in its centroid. So if I know that it extends from this side 6 units inwards and then another 6 units inwards, I'm saying that the total side length of a cube is 6. So as soon as I know the side length, that makes my life a lot easier. So the volume of the big box, or the big cube, is equal to 12 cubed, or 1728. Okay, so that's the first half of the problem. Now the second half is a little bit more intricate. So I'm going to start with that sphere. Okay, I'm not going to mark this right now, but the idea is that I now put a cube inside of this. So I'm thinking that it's something like this, and goes back, goes down, in, up, and something like this. Okay, and then if I want, I'll just kind of maybe sketch in a great circle here. Alright, so this is a cube that sits inside, and I know that the radius is 6. So from this center point, the distance, and I'm going to go to an edge on, or a vertex on purpose, because I know each of the vertices touch the surface of the sphere. So this distance is 6, and this distance is also 6. Okay, so really what that's telling me is that the space diagonal in this case is 12. Okay, and as we studied, or as we found out in let's see, when we were talking about prisms, for a space diagonal of a cube, in that section we said that the space diagonal, its length, is equal to the side times square root of 3. So if you go ahead and solve this, we get that the side length is 4 square root 3, and then therefore the volume, which is just 4 square root 3 cubed, this ends up being 192 square root 3. Okay, so the idea with this problem is that I started out with a figure that I knew pretty well. I started out with this complex scenario, right? I had a cube, and then a sphere inside of a cube, and then a cube inside the sphere, and I broke it up into a couple different problems and broke it into more manageable steps. So I first considered the case where I just have a sphere inside of a cube. Okay, found the volume in that case for the cube, and then with that in mind, I found the volume of the cube that was inside the sphere. Okay, so breaking it up into multiple pieces is sometimes a useful plan of attack in these problems.